So this video is going to expand on one particular issue that is endemic to neuroimaging research. And while those in the field have been a lot better about it in recent years, the problem's still pretty widespread and easily missed, even though it can introduce some pretty huge, gaping flaws in scientific reasoning that can undermine the conclusions of a lot of research. So we'll be talking about what's called the reverse inference fallacy. But first, let's start with a story. A while back, a neuroscientist named James Fallon was doing a brain imaging study on dementia, and they needed control participants, people without dementia, to also get their brain scanned. So for one of those, he himself volunteered. However, when looking at the scan of his own brain during that study, he noticed abnormally low levels of activity in certain parts of the frontal lobe. Now, previous research had shown that these areas are usually active when someone's feeling empathy and doing moral reasoning. He also knew that psychopaths are abnormal when it comes to empathy and moral reasoning. So he concluded he must himself be a psychopath. He actually went back and found out in his family history there was a serial killer in there. So he started thinking, oh my God, genetically, I'm a psychopath. It led to a whole TED Talk, a bunch of interviews, a book, you name it. You can see a Smithsonian magazine right up on the left here. As they say at the bottom, compared to a control brain, James's brain showed significantly decreased activity in areas of the frontal lobe linked to empathy and morality, anatomical patterns that have been linked with psychopathic behavior. Now, the term linked to or linked with is doing some major work here and kind of hiding some pretty sloppy thinking, and I want to show you why. So, forget James Fallon for a minute. Meet cardiologist Jim Failing, a heart surgeon doing a study on how activity in the heart relates to emotion. So in our, it's a part of our biology, just like the brain, we have a heart, right? And he wants to study how heart activity relates to something psychological like emotion. Now, previous research done in his laboratory had clearly shown that when someone is feeling the emotion of fear, having that psychological state, their heart beats fast. So if you're afraid, your heart beats faster than normal. So fast heart rate, we could say, is associated with fear. Science has already shown that. But something interesting happened one day to Jim when he was home with his wife. So he had his wife wired up to a heart monitor for a few days to gather some control data for a study he was doing. That evening, when he and his wife were getting it on, he heard beeping from the heart monitor notifying that her heart rate had gone up way above normal. Her heart was beating really fast during sex. Now, he knew from previous research, like we saw at the top here, that a racing heart indicates fear. So he concluded that his wife was afraid during sex. That heart racing implies fear. Now, this is a silly conclusion to make, right? Because people's heart can beat fast for a lot of reasons, not just for fear. If someone's heart is racing, they might be afraid, or they might be exercising, or they might be enraged, or they might be having sex, or they might have done too much cocaine, or even just too much caffeine. The fact that their heart is racing is not exclusive to fear, even though it's associated with fear, right? So Dr. Jim here made a logical error, just like Dr. James Fallon, the neuroscientist, did. So in formal logic, we actually call this fallacy, it's called affirming the consequent. Here's an example to show you why that reasoning is wrong. That pattern of reasoning doesn't work. So if it's raining, then the sidewalk will be wet. So rain implies a wet sidewalk. That much is true, right? We know that that's the case. But knowing that, what happens if tomorrow my roommate runs into the apartment and she says, oh, I almost slipped out there because the sidewalk is wet? Does knowing that the sidewalk is wet prove that it's raining outside? If you think about it for just a minute, you'll probably realize, of course not, because the sidewalk could be wet due to other reasons, like a neighbor's sprinklers are on, or a water main that busted, or any number of other possibilities. Someone's just having fun power washing to make a fun power washing video online. Who knows? It might be raining, sure, but we can't conclude that it's raining for sure just from a wet sidewalk. Or another example of affirming the consequent, we know that dogs have 4 legs, right? Now, knowing that, if I visit my friend and see her cat, I'm going to notice her cat has 4 legs. And if I'm James Fallon, Does that mean I might assume that the cat must be a dog? Of course not. That's a logical error. But that's the kind of thing we can easily slip into. We see this kind of reasoning mistake all the time in neuroscience, and especially in kind of popular interpretation of neuroscience results. So for example, we know that when someone is afraid, when someone's in a fearful situation, having the fear emotion, there is extra activity in the amygdala, an area of the brain, right? Tons of previous studies have shown that fear is associated with amygdala activation. That's actually true. And now imagine I'm doing some completely unrelated study where I'm scanning people's brains during my other task. So let's say I've got people playing the game Counter-Strike while they're in a brain scanner. Maybe I'm testing some hypotheses about visual processing and reaction time or something like that. But one thing I notice when I'm looking at my data later is that all my participants, they had activation of the amygdala while they were playing Counter-Strike. Whoa! That means video games make people scared, right? Or that fear drives video game performance. I've got to go publish this result in a scientific journal because I've just shown that shooter games like Counter-Strike are associated with fear, right? Except hopefully you're recognizing the logical problem here. The amygdala activates for lots of different reasons, not just fear. So if it's active during Counter-Strike, it could be for many other reasons. We haven't actually connected Counter-Strike and fear, even though we showed that Counter-Strike activates the brain area associated with fear. What we've done in that Counter-Strike study, and what James Fallon did in interpreting his own frontal lobe activation patterns as being a psychopath, was something called reverse inference. Now, forward inference is something that actually makes a lot of sense. Forward inference is like you have someone do a task, doing some cognitive function. Like you have them do language tasks while they're in a brain scanner, or math tasks, or have them meditate, or get them fearful. Whatever it is, you have some cognitive function going on, some psychological process, and then you scan their brain, and you can see what brain areas become active or less active when that psychological state happens. That's forward inference, and it makes sense. But the problem arises when we try to do that in reverse, when we look at certain brain activity, and from that try to infer what psychological state a person is in. So to give you an example of this mistake, how it can go wrong, there's an area in the brain called the insula. It's kind of tucked in behind the frontal lobe, more towards the middle of the brain. Now, in previous studies, we've actually seen that the insula is activated during perception, during motor control, like movement control, during tasks involving self-awareness and interoception, like knowing about what's going on within your gut and things like that. The insula is active for a lot of emotional tasks, emotional experiences, so it's associated with emotion. It's active for interpersonal experience, like social stuff. It's active when we're detecting salient stimuli, like figuring out what kind of stands out in the environment, and lots of other things, actually. We see the insula activate for a ton of different psychological processes, okay? Now, the insula, it's active for all these different psychological activities, but imagine I'm doing some neuroscience study. I'm doing some other neuroscience study. I've got participants in a brain scanner. Maybe they're doing memory tasks. And during one session, an experimenter in the room keeps, farting. Okay. So they're in the brain scanner doing memory tasks. Just all my participants, they come in, they do a memory task in the brain scanner. But today, the experimenter ate something crazy the night before. And so that experimenter in the room with one of my participants is just farting up a storm in the fMRI room. The participant, during their experiment, keeps smelling these farts, right? And I notice on their brain scan data, when I look at it later, I notice on the brain scan, the insula was active during the trials when the experimenter farted. Holy crap, so to speak. I've discovered that farting is an emotional activity. Why? Well, because past research has shown that the insula is active for emotion. And here, the insula is active when they're smelling farts. So it's proven that farts cause an emotional reaction, right? It's all here in the brain scans. Except we know that the insula activates for a lot of reasons other than emotion, including basic perceptual processes, which would include smelling, right? So it may have been active just because the person was smelling. In fact, emotion might not have been involved at all, even though I see that area of the brain active, and it's an area that tends to be active during emotion. So knowing the insula is active in a certain situation doesn't let us conclude that the person had some mental state that's been previously associated with the insula. That would be a fallacy, a mistake, the reverse inference fallacy. So we could define the reverse inference fallacy basically as reasoning backward from observed brain activity during one task, like we're having them do function A, right? We're having them do task A. Reasoning backward from brain activity to a different cognitive process, function B, right? Something we're not measuring directly, based on some past research that showed function B also activates that brain area. So the fact that we know that brain area activates for function B, and we're seeing that brain activity now, it's a fallacy for us to reason backward and say, because I'm seeing that brain activity, they must have that cognitive process. They must have function B going on. And this happens, we make that mistake even though we haven't measured function B directly. We haven't actually verified that function B is happening or that psychological state B is happening. We're just assuming it. We're making a false inference here, or at least going beyond the data we have. We're making an inference that's possibly false by assuming that psychological state or function B is happening just because the brain activity is happening that usually goes with it, right? So basically, when you see a given brain area activate, when you see a given brain area be like extra active or less active than usual or whatever, just be careful not to assume that you know what psychological process is happening from that brain area being active. Another way to see this issue, imagine we do like a big genetic study of people with schizophrenia, and we find that all of them have this particular genetic variant, maybe a particular allele on some gene that's common to every person with schizophrenia. We have found a gene that's associated with schizophrenia. But does that mean we have a biomarker of schizophrenia? Like, can we diagnose someone as having schizophrenia simply because they have that genetic variant? No, that doesn't work, because a ton of people without schizophrenia might also have that same genetic variant, right? It's only going to work as a diagnostic marker if the variant only happens in people with schizophrenia. But that's not necessarily the case. Even if everyone with schizophrenia has it, that still wouldn't prove that someone having it has schizophrenia, because other people might have that same genetic variant without schizophrenia. Well, the same issue has happened with cognitive neuroscientists who are using brain scans to study schizophrenia. So when we compare people with schizophrenia to control participants in brain imaging, like using PET scans like you see here, or fMRI scans or something like that, we do find significant differences in brain structure and in brain activity. People with schizophrenia do show some distinct patterns of brain activity. But then it's surprisingly common for researchers or for people reporting on scientific results to mistakenly assume that if we see that type of brain activity or those brain areas being more active or less active, that the person must have schizophrenia. But that doesn't work. That reasoning is wrong. That's not a valid deduction, because there may be other reasons why people have that pattern of brain activity. Like maybe those activity differences happen in a lot of psychological disorders, not just schizophrenia. So someone having it on a brain scan doesn't narrow down which disorder they have. But also, that same kind of activity might happen in the brains of people with no disorder at all. It might just be one type of normal variation that happens to also go along with schizophrenia. In that case, we shouldn't jump to any conclusion about psychological disorders just from a brain scan like that. Now, as I said, researchers working in neuroscience are aware of this issue. Like you can see in this 2020 review article here, that people in the schizophrenia neuroscience community are working to fix this issue. They're aware of it. It's actually been pretty widely recognized in cognitive neuroscience since this researcher, Russ Pauldrick, brought it up formally in 2006. But the issue still pervades like a surprising amount of cognitive neuroscience, because it's often a little more subtle than the examples I've given here. So I don't know. For example, it might be that we see a certain pattern of brain activity during, say, an intense religious state. And that brain activity looks a lot like what we see in schizophrenic patients who are hallucinating voices, showing kind of higher or lower activity in the same places as in their brain. From that, a researcher might hypothesize that these religious experiences are a similar cognitive state to schizophrenic hallucinations. That's the kind of thing that might show up. I'm making this up, right? But that's the kind of thing that might show up in the research literature based on some data, based on brain scans of what we see when people are having a certain type of really, intense religious experience. And it's like, oh yeah, that looks like the brain scans we see with schizophrenic patients. That's the kind of reasoning people use all the time. But that may actually be a stretch because those brain areas might be involved in lots of things, not just auditory hallucinations. So it's a mistake to assume that people with this religious experience are having auditory hallucinations or something like that. Let me give you just a couple more examples before I end this. So imagine the following study. People with PTSD do math by visualizing unicycles, published by R. Inference and A.T. Consequent. So the abstract of this made-up study that I made up says, our study scanned the brains and bodies of 46 volunteers with PTSD while they did simple math problems. So it's just a study of people with PTSD doing math, maybe how their brains look different when they're doing math compared to control participants, right? And here's what they say. They scanned not just the brain, they also scanned the body. So they found, heart and lungs and stuff like that. So we found that the lungs were active for those with PTSD doing math. In other words, they were breathing while they did math. Past research has shown that people breathe using their lungs when they are visualizing old memories. Smith et al., 1995. And that's true, right? When people are visualizing, they're also breathing. And other research has connected breathing to riding a unicycle. So like WENZ 2009, where they measured over 200 experts and novices unicycling and found that every single participant in their study was using their lungs during the task. Because of course we breathe when doing anything. So since our PTSD volunteers were using their lungs while doing math in our study, we conclude that people with PTSD do math by visualizing past memories of unicycles. Like, that's a stupid, silly example I made up, but you can see how it's a mistake to just notice a physiological process happening and assume that you know what cognitive or psychological state is going on just because some past research found that that physiological process happened during a particular psychological state, right? We've done a reverse inference fallacy here. However, since no one realized the error made by those fictional authors I just made up in the last example, they ended up publishing more crappy science afterward. Like this example. Cooperation comes from anger. By the same authors, right? And again, I just made this crap up. But the abstract here might read, our study scanned the brains, so they're doing neuroscience now. Our study scanned the brains of people choosing to cooperate or choosing to betray the other player in an economic decision-making game called the Prisoner's Dilemma. So we're having people do this little game where they can choose to cooperate or betray the other person, and they're in a brain scanner while they do this game, okay? We found that during cooperation, so the trials when people did end up cooperating, we found that during cooperation, the amygdala was active, suggesting that cooperation comes from anger, because past studies have shown that the amygdala is associated with anger. Like Johnson 2003 found that the amygdala is active during road rage, and Iglesias 2017 showed that calling someone an idiot also activates their amygdala. Therefore, based on our cool and expensive brain imaging study, we conclude that cooperation is based on anger. Now, yikes, right? That's bad reasoning. Like, just because the amygdala is active during anger doesn't mean that when we see amygdala during our study, it's anger that's going on. That's the reverse inference fallacy striking again. The fact that the amygdala was active during some task does not tell us for sure what psychological process is going on, even if we do know there are psychological processes like anger that are previously associated with the amygdala. So just remember it this way. Even if a psychological process or a cognitive task consistently leads to a certain brain area being active, that doesn't mean that when the brain area is active in some other circumstance that we can assume the same psychological process is going on. Or, as logicians have known for thousands of years, just because A implies B doesn't mean that B implies A. That's the general fallacy of affirming the consequent. And the reverse inference fallacy is just a subtype of that. Now, is there ever a time when reverse inference is okay? One, it's a deductive fallacy. Like, we know it is bad deductive logic. It doesn't work. We can't prove a psychological process from a brain state. But If we use it carefully, mindfully and carefully in certain circumstances, reverse inference can be useful for some inductive reasoning, where we kind of come up with hypotheses to generalize from the data that we're seeing across a bunch of different circumstances. So in other words, it can make sense in some cases to infer a cognitive process based on what brain activity we're seeing. If, let's say, we're doing meta-analyses combining a bunch of studies, like if you find across hundreds of studies that one specific little part of the fusiform gyrus at the bottom of the temporal lobe, if that part is active in every study that involves people looking at faces, but that brain area in the fusiform gyrus is not active for any non-face tasks, and we've tried this across a bunch of different studies, then you might become more confident that it really is a face area in the brain. And in that case, if you find that it's active during some other task, like a type of memory task that you're testing, it might be reasonable to conclude the person is thinking about faces during that memory task, because we're so sure that that's a face area, right? That makes some inductive sense, although we have to do a ton of different studies and different contexts to get confident that that area is really specific to faces. But even then, it's still not a proof. It's still not foolproof deductive reasoning, because we might later find that, say, that little area in the fusiform gyrus, maybe it's more nuanced. Like maybe it's not specific to faces, but to anything we have years and years of experience distinguishing visually, right? So that would be faces, sure, but maybe we also later discover that that little brain area, that so-called face area, maybe it's also active when like a expert bird watcher is telling apart individual birds, or when an expert mechanic is visually distinguishing cars. Maybe it's just like a visual expertise area or something like that. And we missed that when we were just noticing how it's very selective to faces. And anyway, also, I should add the reasoning with reverse inference, it becomes stronger the more we can show that the brain activity we're talking about is selective to that cognitive process or to that, psychological state, that it's specific to this thing, that it basically only happens for that process. Then it's stronger. Then, once we've convinced ourselves of that, then it's okay to say that, see the brain activity in some other context and be like, okay, I know what's going on. That brain activity, I can conclude such and such cognitive process must be happening. But also, at that point, we should probably just measure the cognitive process more directly instead of trying to infer it from brain activity. Like rather than looking at a brain scan and saying, this looks like a depressed brain, so I have a biomarker of depression. Honestly, that's stupid because it's 1,000 times cheaper, 1,000 times easier and faster and more accurate to, give the person a depression inventory or have them talk to a qualified clinician. We don't need the brain scans for that. But anyway, it makes more sense to directly measure the thing, the cognitive state, the psychological process, or to get it through other data in addition to the brain scan if we want to be confident that that brain activity does actually imply the cognitive state we're assuming. Meanwhile, as things like machine learning and big data sets of millions of brain scans get combined together, we can use pattern recognition algorithms to get quite a bit of predictive validity just in terms of predicting cognitive states from brain states. So that's reverse inference, but it's not the same as, we're not explaining cognition. We're not getting into the mechanisms in that case, but predicting cognition can still be a valuable part of the puzzle. And that's something we can potentially do if we have a big enough data set and we run it through something like machine learning. So there is some value to reverse inference in some cases, but as usual, it's not about in a single study, we see this brain area active and we can be sure what's going on. Rather, we kind of have to bring together a lot of different data to make those conclusions. Also, just to be clear, this is a problem for all of psychology, not just neuroimaging. Anytime we infer a psychological process from some observable behavior, we might make this exact same error. So let me demonstrate how this could happen with anything we observe and conclude from that observed behavior that there's some psychological state going on. Like feeling anger, that's an internal psychological process, a mental state. It's a cognitive thing, right? That can lead to an observable behavior like yelling behavior, right? So anger, internal psychological state, leads to yelling, an observable behavior. That's our data. That makes sense. We might see that over and over again and be like, yeah, anger leads to yelling. So if I see someone doing yelling behavior, can I conclude that they are currently experiencing the emotion of anger? You might initially think, yeah, of course, but no, because they might be yelling in excitement that their sports team won, or yelling to their friend across the parking lot so they can hear from far away, or yelling because they're part of a yelling competition on TV, or for any other number of reasons, right? So if we observe yelling during an activity, if we observe that behavior, we shouldn't automatically conclude that the activity makes people angry. That would be the reverse inference fallacy, even without any neuroscience brain scans involved. So this isn't specific to neuroscience, it's just common in brain scan studies. But if an observable behavior or a brain state is super selective and it only happens for that one cognitive function, if we're sure of that, then we can use reverse inference. We can conclude the cognitive function is happening just from observing that behavior or just from observing that brain state. So reverse inference is only valid when kind of the previously established connection is super selective, when the correlation is nearly perfect and the brain state plus cognitive function go together kind of 1-to-1. Like if there's maybe a really distinct sound pattern to angry yelling that makes it different from the sound pattern of all other yelling, then when we hear that specific sound pattern of yelling behavior, we could indeed conclude the person is in an angry psychological state. Like reverse inference would be pretty valid in that rare case. But even then, an actor in a TV show could perhaps do that specific type of yelling behavior without being in that psychological state. So even then we should kind of beware. Anyway, that concludes our cognitive neuroscience topic. In the next topic, we'll have some videos diving into one of the most basic and really fundamental cognitive processes, which is perception. The way our brain makes sense of and interprets the information coming in through all of our sensory channels and turns it into a perceptual experience.